November 20th, 1944, Manchuria. The sound of the engines faded over the snow-covered hills near the city of Mukden. On the ground, Japanese soldiers surrounded a massive aircraft, unlike anything they had ever seen. Its silver fuselage stretched longer than any bomber they had encountered. The markings were American, but the crew was gone, either captured or lost in the crash landing. The aircraft was a Boeing B-29 Superfortress, one of several that had been forced down during bombing raids over Japanese territory and Manchuria. Within hours, word reached Tokyo, and then Berlin. The Allies had sent a machine so advanced, so far beyond the reach of Axis engineering, that it would soon trigger one of the most secret technical studies of the entire war. The aircraft's sheer size was staggering, a 141-foot wingspan. 4 Wright R-3350 engines, each delivering 2,200 horsepower. It could cruise higher than 30,000 feet, faster and farther than any bomber the Axis possessed. The Japanese Army Air Technical Intelligence Department began documenting every feature of the wreck. They measured the wings, photographed the cockpit, and removed panels to study the strange honeycomb structures inside the fuselage, lightweight yet incredibly strong. What they didn't yet know was that this single crash would soon draw the attention of German engineers half a world away, who would receive copies of every report and photograph through the intelligence-sharing network that still linked Tokyo and Berlin. In Germany, the winter of 1944 was already desperate. Allied bombers filled the skies daily, and the Luftwaffe was running out of fuel, pilots, and time. German engineers had seen American bombers before: the B-17 Flying Fortress, the B-24 Liberator. But this new aircraft was different. The reports arriving from their Japanese allies described something that read more like science fiction than a conventional bomber. A pressurized cabin allowing crews to fly in shirt sleeves at altitudes where Messerschmitts struggled to breathe. Remote-controlled gun turrets, operated electrically with gyroscopic aiming. A wingspan rivaling a small airliner, and a range that could reach from the Marianas to Tokyo and back again. Inside Germany's Air Ministry, technical officers began to ask questions that made even the most loyal engineers uneasy. How had America built such a machine in such numbers, with their factories untouched by war, while German production lines fought shortages of every basic material? The Reich Aviation Ministry ordered its technical office, the Technisches Amt, to analyze every scrap of information arriving from Japan. Drawings, photographs, recovered engine parts, even fragments of alloy plating were studied under microscopes at the Luftfahrtforschungsanstalt in Brunswick. Engineers who had once designed the Heinkel 177 and Dornier Du 217 now sat quietly over American blueprints, realizing with each passing hour that they were looking at something built in another industrial universe. The reports from Manchuria reached Germany in December. Among the most detailed came from Harbin, where Japanese technicians had reassembled portions of a relatively intact B-29. The aircraft's serial markings were traced back to the 462nd Bomb Group, lost during raids over Manchuria in late 1944. The Japanese codenamed it the B-san, meaning B-3. They documented the aircraft with painstaking precision: every bolt diameter, every gear housing, every instrument marking. Then they shared the full dossier with their German counterparts through diplomatic couriers traveling the Trans-Siberian route before it was cut off by the Soviet advance. When the first full technical drawings arrived in Berlin, senior engineers at Junkers and Heinkel gathered for what they expected would be a routine intelligence briefing. What they saw instead left them in stunned silence. The B-29's pressurization system alone was more advanced than anything in German aviation. Its remotely operated turrets used analog computing sites that calculated lead, range, and deflection automatically, something Germany had experimented with but never deployed successfully. Its enormous bomb bay doors opened and closed with electric motors rather than hydraulic pumps, saving weight and improving reliability. Even the wiring looms were manufactured with an organization and clarity that suggested a kind of industrial discipline no German factory could match under wartime conditions. One engineer described it in his report simply, "This is not an aircraft. It is an industry in the shape of an aircraft." The phrase circulated through the Air Ministry in whispered admiration and disbelief. What Germany was witnessing was not just superior design, it was superior manufacturing philosophy. The B-29 was the product of an entire ecosystem of American industry, where precision tools, standardization, and production planning were as advanced as the aircraft itself. The most shocking detail for German engineers wasn't even its technology. It was that the Americans were already producing hundreds of them. Boeing's plants in Wichita, Bell's facilities in Georgia, and Martin's in Omaha were delivering one Superfortress every hour at their peak. To the German mind, that figure was impossible. The Luftwaffe had produced just 1,400 of its most advanced bomber, the Heinkel He 11-1, across several years. America was building a machine twice as complex, faster than Germany could repair the ones it already had. At Peenemünde, engineers tasked with developing long-range weapons for Germany's last hope, the V-series missiles, studied fragments of the B-99's aluminum alloy. They found it lighter, stronger, and more resistant to corrosion than any domestic equivalent. The secret lay in the composition, 75 St6 aluminum, a high-strength alloy produced in massive quantities by Alcoa using heat-treating methods Germany couldn't replicate at scale. Metallurgists submitted desperate memos proposing similar research, but by late 1944, the country's scientific resources were being redirected to emergency weapons projects. The few surviving Luftwaffe test pilots who saw the B-29 reports compared it to something from the future. The aircraft's high-altitude performance meant that almost no German interceptor could reach it. The Me-262 jet could climb that high, but not for long, and its short endurance made interception nearly impossible. Even the revolutionary Me-163 rocket fighter could only remain airborne for minutes. The B-29, meanwhile, could fly for 3,000 miles without refueling, with full payload and crew comfort. By the time the first Allied formations of B-29s began their devastating raids on Japan from bases in the Marianas, German observers already knew what was coming. Through their liaison network, they received first-hand accounts from Japanese officers describing cities erased in hours by bombers flying so high that anti-aircraft fire couldn't reach them. The engineers in Berlin realized that if the war had been reversed, if these bombers had been turned toward Europe instead, there would be nothing in the German arsenal capable of stopping them. That realization, the simple understanding that they were now decades behind, began here, in the winter of 1944, in a quiet analysis room at Kummersdorf, as German engineers traced the blueprints of an American aircraft that symbolized the end of their technological dominance. January 1945. Kummersdorf. Proving ground, 25 kilometers south of Berlin. Snow drifted across the long concrete taxiway where Germany's remaining test aircraft sat idle. Inside a dimly lit hangar, a group of Luftwaffe engineers huddled around tables stacked with Japanese reports, American blueprints, and a handful of salvaged B-29 components that had finally arrived through diplomatic channels. The war was collapsing outside those walls, rail lines destroyed, cities burning. But here, the work continued. The engineers weren't testing weapons anymore. They were studying what the future looked like, and it had 4 massive engines, a pressurized fuselage. One of the first parts to arrive was a section of the B-29's remote-controlled gun system. It consisted of a compact electric turret with a pair of .50 caliber Brownings and a compact gyroscopic sighting computer. German engineers had designed remotely operated systems before, notably for the Me-210 and 410 twin-engine fighters, but none approached this level of sophistication. The American unit used a mechanical analog computer driven by servos that automatically adjusted for airspeed, altitude, and deflection. A gunner could target an enemy plane visible only through a periscope and hit it, while the bomber maintained level flight at over 30,000 feet. At Junkers Darmano Design Office, the engineers assigned to evaluate the B-29's defensive systems sent a brief report to the Air Ministry that stunned even hardened bureaucrats. "We have examined the American fire control installation recovered from the B-2 bomber. The design is entirely modular. Components are standardized and interchangeable. The aiming computer functions in all positions with minimal calibration. It is industrial engineering at a scale and precision we cannot reproduce." The phrase industrial engineering reappeared repeatedly in the internal correspondence of German aircraft manufacturers through early 1945. It reflected a truth that was becoming inescapable. America's greatest weapon was not the machine itself, but the system that could produce it. The B-29's central pressurization system became another revelation. American engineers had divided the fuselage into separate sealed compartments, one for the flight crew, another for the gunners, and a third for the tail section. These compartments were connected by a narrow pressurized tunnel running above the bomb bays, a lightweight aluminum tube just large enough for a man to crawl through. German designers examined the blueprints with disbelief. The sealing mechanisms used neoprene gaskets, flexible and heat-resistant, materials unavailable in wartime Germany. Even the windows were multi-layered plexiglass treated to resist fogging, another American innovation born from consumer industry rather than military research. The most shocking discovery came when engineers studied the aircraft's electrical system. The B-29 used a fully integrated 24-volt DC network with centralized distribution panels that resembled those found in power plants, not aircraft. Every major system, from the turrets to the bomb bay doors, drew from a redundant power bus designed for easy maintenance and rapid replacement. German aircraft, by contrast, used decentralized wiring with little standardization. Each model required unique connectors, custom relays, and hand-built wiring looms. The B-29's layout looked more like something designed for an assembly line than for an airplane. It was built to be reproduced, not just designed once. By February, the engineers at Kummersdorf had compiled enough comparative data to create a full technical monograph titled Erkenntnisse aus dem B-2 Bomber, Findings from the B-2 Bomber. The report circulated through the Luftwaffe's technical bureaus, though few officials had the courage to read it in full. It made for uncomfortable reading. The study concluded that the American bomber's manufacturing tolerances exceeded those used in German military production by 40 to 60%, meaning that every part fit perfectly with minimal adjustment. The Americans achieved this by using precision jigs, factory-controlled environmental conditions, and workforce specialization unheard of in Germany's dispersed and bombed-out production network. The report went further, comparing material usage. The B-29 structure incorporated magnesium alloys for weight reduction and honeycomb panels for stiffness, materials that Germany had experimented with but couldn't produce at scale due to shortages and safety hazards. The American heat treatment methods for aluminum, standardized by Alcoa, produced uniform strength across thousands of airframes. German engineers had to rely on batch-by-batch testing, introducing inconsistencies that plagued aircraft like the Me-262 and He-177. One of the most respected German engineers to review the findings was Dr. Waldemar Voigt, a key designer at Messerschmitt. He had spent years refining the Me-262 jet, a revolutionary aircraft in theory, but one plagued by manufacturing delays and engine reliability problems. When Voigt examined the B-29 documentation, he saw immediately what Germany had failed to achieve: complete system integration. Every component, from the engines to the gunnery computers, was designed to fit into a broader production philosophy. "It is not the machine that defeats us," he wrote privately to a colleague, "but the method of building it." The German test pilots who read through translated accounts from Japanese crews were equally struck by the descriptions. The B-29's Wright R-3-350 engines produced nearly 9,000 combined horsepower and used a sophisticated turbo-supercharging system that maintained full power at 30,000 feet. The reports from Manchuria claimed that the bomber's power plants could run for hundreds of hours with minimal maintenance. In Germany, the Junkers Jumo 213 and BMW 801 radial engines often required overhauls after just 50 hours of flight. The American engines had achieved what German mechanics considered impossible, both power and reliability. Meanwhile, across the collapsing Reich, production managers at aircraft factories were beginning to receive fragments of the Kummersdorf findings. For those who still believed Germany could recover through wonder weapons, the B-29 became an unspoken symbol of defeat. Not because it was invincible, but because it represented a kind of industrial civilization that Germany simply could not match anymore. By March 1945, even as Allied troops crossed the Rhine and Berlin's defenses crumbled, engineers continued to study every new photograph and diagram sent from Japan. They knew the war was lost, but curiosity persisted. Some of them quietly admitted that what they were seeing wasn't just a weapon of war, it was a blueprint for the post-war world. March 10, 1945. Night had fallen over Kummersdorf. Air raid sirens wailed in the distance as Berlin burned under another Allied bombing run. But inside the underground technical laboratory, the work continued by candlelight and battery lamps. Engineers huddled over thick stacks of translated Japanese documents. On the table lay an American instrument cluster from a B-29 cockpit, one of the few surviving artifacts that had arrived through diplomatic pouch before the routes were closed. They studied it not for combat value, but as evidence of something deeper, how an enemy built machines that functioned perfectly, even under pressure. The B-29's instrument panel impressed the Germans for its simplicity and clarity. Each dial was labeled with precision. Controls were logically grouped and standardized across every production block. To the engineers who had worked on Luftwaffe bombers, this was revolutionary. German cockpits, even on the most advanced models, were filled with hand-marked switches, improvised placements, and non-standard gauges from different suppliers. American standardization was absolute. Every B-29 pilot trained on a simulator identical to his aircraft. Every gauge, throttle quadrant, and circuit breaker had the same feel, whether built in Wichita or Omaha. It meant fewer mistakes, faster training, and better survival odds. And it reflected a philosophy the Germans had never achieved, manufacturing for interchangeability, not individuality. The Germans had long prided themselves on precision craftsmanship. Each airplane built by a team of skilled mechanics who understood the feel of every bolt and the tone of every instrument. But that pride came at a cost. Production rates were slow, parts were unique, and repairs required experts. The Americans had taken the opposite route. They had industrialized consistency, sacrificing individual craftsmanship for mechanical reliability and speed. As one German officer wrote in his notes that March, "Their genius is not design, but system." Engineers at Junkers analyzed the B-29's flight control systems next. What they found stunned them again. The aircraft used boosted hydraulic control surfaces, an innovation far ahead of its time. The massive bomber could be flown with fingertip pressure, even at high altitude, while Luftwaffe pilots wrestled with control forces so heavy that long missions left their arms numb. The B-29's system used dual redundant pumps, each capable of powering the controls independently. If one failed, the other took over automatically. German engineers had designed similar systems for experimental aircraft, but never managed to field them. Their materials and seals couldn't handle the required pressures reliably. The B-29 had solved those problems years earlier, with parts mass-produced by civilian suppliers who had been building hydraulic machinery for automobiles and factories long before the war. Another discovery struck deeper still: the bomber's maintenance philosophy. The B-29 had removable engine cowlings, quick disconnect wiring harnesses, and standardized mounts for rapid engine swaps. Ground crews could replace an entire Wright R3350 engine in hours. German ground crews, by contrast, spent days servicing complex inline engines that required careful disassembly and tuning. The American philosophy wasn't to repair in the field, it was to replace fast and keep moving. That was the same principle behind the Sherman tank's design, the Red Ball Express truck convoys, and now, even in the air, it defined the B-29. Among the engineers who reviewed these findings was Dr. Karl Bauer, a test pilot and engineer who had flown the Me-262 and evaluated numerous Allied aircraft during the war. In his later writings, Bauer recalled his disbelief upon seeing the B-29's structural drawings. It was an airplane that represented the future of engineering, large-scale system integration. The machine was not designed for a few exceptional pilots. It was designed for an entire industrial system to support and reproduce. At the same time, across the world in Japan, their engineers were attempting to replicate the American bomber. They had recovered multiple B-29s that crash-landed during missions over the empire, some nearly intact. These aircraft were reassembled at the Tachikawa and Mitsubishi facilities outside Tokyo, under the direct supervision of the Imperial Army Air Technical Research Institute. They called the project Kenkoku-Go, the national defense plane. The Japanese engineers were brilliant, but what they discovered mirrored what Germany was realizing. They could copy the form, but not the function. The B-29's pressurization components required rubber compounds Japan didn't possess. The plexiglass was chemically treated in ways their factories couldn't reproduce. Even the rivets were a mystery, high-tensile, heat-treated alloys formed with precision machines unavailable in Japan or Germany. Every attempt to duplicate the systems exposed another missing link in their industrial chain. The Japanese sent a complete report to Berlin in February 1945, summarizing their conclusions. We can reproduce no more than 60% of the airframe by available methods. Essential materials and tooling do not exist within the empire. When that report reached Germany, it effectively confirmed what Kummersdorf's engineers already knew. The Axis powers were fighting in the mechanical present. The United States was operating in the industrial future. Still, the Germans persisted. They took what they could learn and applied it where possible. The Heinkel Design Office studied the B-29's high-aspect wing design, noting the efficiency of its laminar flow surface. They tried applying similar techniques to the He-277 bomber prototype, though it would never fly before the war's end. The electrical engineers at Siemens analyzed the turret control servos and proposed using the principle for future jet projects. But none of these small insights could bridge the industrial divide that the B-29 represented. The scale of American production continued to grow even as the war neared its conclusion. By the spring of 1945, the United States had produced over 1,600 B-29s. Japan, under constant bombardment, had managed to assemble 2 incomplete replicas of its own, both grounded. Germany had only seen the aircraft in photographs and fragments, yet even those fragments told the story clearly enough. In April, as Allied forces closed on Berlin, one of the last surviving reports from Kummersdorf crossed the desk of a senior Luftwaffe official. It was brief, just a few pages, summarizing months of study and ending with a single observation. The American bomber represents a level of engineering coordination between design, materials, and industry which exceeds our national capabilities by approximately 20 years. That was the sentence that circulated quietly among engineers who would later rebuild West Germany's aviation industry. It wasn't defeatism, it was recognition, a professional acknowledgement that they had seen a glimpse of the future, and it was American. April 20th, 1945. The Red Army was less than 50 miles from Berlin when the last intact set of B-29 blueprints was packed into a wooden crate at Kummersdorf. The engineers labeled it simply Technische Unterlagen, Fernbomber B-San. They didn't know if anyone would ever read it. By then, the proving grounds were nearly deserted. Supply lines had collapsed, and the sounds of artillery rolled across the horizon. Yet a handful of engineers stayed, not out of loyalty to the collapsing regime, but because they wanted to preserve their work, an honest record of what they had learned from studying the most advanced aircraft they had ever seen. In those final weeks, several of Germany's most senior aeronautical engineers gathered one last time to review the findings. Among them were specialists from Junkers, Heinkel, and Arado, men who had designed the jet age into existence but were now surrounded by its destruction. They spread the American blueprints across the table. To them, it wasn't merely an aircraft design, it was a lesson written in aluminum and precision bolts. The B-29 symbolized what they had failed to achieve, not because they lacked imagination, but because they lacked the industrial depth to make imagination practical. They compared notes on the bomber's production methods. The B-29's entire structure was assembled from pre-formed submodules that arrived at the final plant ready to bolt together. Wings, fuselage sections, tail assemblies, and even entire cockpit modules. Each came from a different factory hundreds of miles apart, yet they fit perfectly when joined. The Germans had dreamed of similar distributed manufacturing for years but could never execute it. Their production facilities, bombed and fragmented, relied on hand-fitting parts, manual alignment, and constant recalibration. The Americans, with their vast unbombed territory and abundance of machine tools, had turned aircraft construction into something closer to an assembly line for automobiles. One of the Heinkel engineers pointed to a schematic of the bomber's forward fuselage, where the pressurized crew cabin and nose turret were integrated into a single prefabricated section. "We could not even attempt this," he said quietly. "The jig tolerance alone requires more steel than we have in an entire factory." His remark wasn't hyperbole. German machine tooling had become so depleted that even maintaining precision jigs for the Me-262 had become an exercise in improvisation. American factories, by contrast, could afford to build full-scale alignment frames for every major component of every aircraft type, keeping them stable to within thousandths of an inch across hundreds of production cycles. The engineers also discussed the B-29's electrical systems, not just the complexity, but the confidence with which they had been implemented. Entire subsystems operated electrically, where Germans still relied on hydraulics or pneumatics. The Americans trusted electricity because their manufacturing and quality control systems guaranteed reliable insulation, wiring, and switchgear at scale. To the Germans, accustomed to brittle materials and voltage instability, such design choices seemed reckless, until they realized that it worked flawlessly because the industrial base supported it. The Americans could rely on their infrastructure. The Germans could not. By now, the engineers knew the war was lost, but they continued to write. The final technical summary prepared at Kummersdorf before its evacuation is a remarkably sober document. It compared American, German, and Japanese aircraft engineering philosophies without political commentary. It concluded that American success stemmed from integration between designers, factories, and logistics. "The enemy," it read, "has achieved a complete unity of engineering and production. Their machines are designed to be built. Ours are built to be designed." That single line became a kind of epitaph for Germany's wartime engineering. Their factories had built masterpieces, the Me-262, the Tiger tank, the V-2 rocket, but each was a bespoke creation, beautiful in theory and unsustainable in practice. The B-29 represented the opposite philosophy: practical, replicable, and relentless. As Soviet artillery approached Kummersdorf, several engineers fled west toward American lines, carrying their notes with them. Among them were men who would later work in the aviation industries of both East and West Germany during the Cold War. Many of them would eventually contribute to aircraft like the F-104 Starfighter under NATO contracts, or the early designs that led to the post-war Lufthansa fleet. Nearly all of them, when interviewed decades later, recalled their first encounter with the B-29's technical data as a turning point, the moment they realized what modern industrial engineering truly meant. Meanwhile, on the other side of the world, in the Soviet Union, a very different story was unfolding. In August 1944, 3 B-29s had made emergency landings in Vladivostok after bombing missions against Japan. The crews were interned and the aircraft impounded. Soviet engineers began their own secret study of the American bomber, known as Project B-4. Where Germany had only fragments and drawings, the Soviets had complete aircraft. They took them apart, measured every component, and by 1947 had built an exact copy, the Tupolev Tu-4. It was so precise that American engineers who inspected it years later found even the manufacturing tool marks replicated. The Tu-4 became the foundation of Soviet long-range aviation for a decade, a direct descendant of the B-29 that German engineers had once studied only on paper. When news of the Soviet reverse engineering reached post-war German scientists working under Allied supervision, the reaction was mixed. Some were incredulous, others quietly impressed. The Soviets, unlike wartime Germany, had the manpower, raw materials, and centralized control to replicate what America had done, even if it required copying it bolt for bolt. The lesson was unmistakable. Industrial capacity was the true measure of power in the modern world. By the time Berlin fell, the last surviving B-29 reports were buried under rubble at Kummersdorf, or confiscated by advancing Soviet troops. But a few copies survived. In 1946, Allied intelligence teams recovered several of these documents while cataloging Germany's captured research archives. They were translated and analyzed in London and Washington, becoming part of a broader Allied understanding of what Germany had learned and what it had failed to grasp in time. Inside those reports, the American analysts found something remarkable. No bitterness, no denial, just respect. The German engineers had written about the B-29 with professional admiration, describing its systems in precise technical language, acknowledging superiority without excuses. For them, it had become not an enemy weapon, but a symbol of the engineering future they hoped to join once the war ended. May 1945, the Third Reich was gone. The war was over, and the ruins of Berlin were littered with the twisted skeletons of aircraft that had once represented Germany's technological pride. Among the rubble at Kummersdorf, Soviet soldiers found fragments of reports, charred blueprints, and a single aluminum data plate stamped B-29 Superfortress. The engineers who had once studied it were now prisoners, displaced persons, or new recruits in whatever post-war world would take them. Yet the lessons they had written remained, a quiet record of realization, respect, and humility. The story of the B-29 inside Germany had never been about capturing a secret weapon. It was about witnessing an entirely different civilization of engineering. Every line on its blueprints spoke of a manufacturing system that Germany could never replicate during the war, a nation where machine tools outnumbered tanks, where workers were trained by industry instead of ideology, where engineering was not a collection of geniuses but a synchronized process connecting thousands of minds. In the years that followed, the surviving German engineers who had handled the B-29 documents went on to rebuild their careers in civilian aviation. When the new Federal Republic of Germany began developing its first post-war airliners, many of these same men quietly applied what they had learned from those old American blueprints: modular assembly, standardized wiring, systems integration. They no longer chased theoretical perfection. They designed for reliability, serviceability, and mass production. The B-29 had shown them that these were not compromises. They were the future. Even in the East, under Soviet supervision, German engineers absorbed the same lesson. Many were transferred to work on early Soviet jet programs, contributing to designs that borrowed directly from the B-29's integrated systems approach. The bomber they had once studied in disbelief became the unseen teacher of a generation. When the Allies published post-war intelligence reports summarizing Germany's technical findings, one line stood out among all others. It came from an internal memo dated January 1945, written by a German materials scientist after examining B-29 alloy samples. He wrote, "Their metal is not extraordinary, but their process is perfect." It was perhaps the most accurate sentence written about the war's industrial balance. America had won not by inventing miracles, but by perfecting methods. The B-29 itself became more than a weapon. It was a bridge between eras. It was the last piston-powered giant and the first true modern aircraft, designed on production blueprints, not drawing boards. It carried the world from the age of handmade machines into the era of precision systems built by factories that never slept. And for the engineers in Germany who studied it during those last desperate months, it was like peering into the future through the wreckage of the present. One of them, an aeronautical engineer named Hans Müller, later interviewed in 1963, remembered the moment he first saw the American schematics spread across the table at Kummersdorf. He was 31 then, a gifted designer who had worked on experimental high-altitude bombers. "We were not angry," he said softly. "We were astonished." It was like seeing what flight would look like 50 years later. We realized, perhaps for the first time, that the war was not just being fought with weapons. It was being fought with factories. And we had already lost that war before it began. In the United States, production of the B-29 ended in 1946, but its influence continued through the Cold War. The aircraft's systems laid the foundation for the B-50, the KC-97 Stratofreighter, and even early jet bombers like the B-47. Each borrowed not just its design, but its production philosophy: modular, standardized, industrially scalable. The same approach that had stunned German engineers became the model for the post-war aerospace industry worldwide. By the time the first jetliners crossed the Atlantic, the principles that built the B-29 were everywhere: in civil aviation, in factories, and even in the maintenance manuals written decades later. And somewhere in that legacy were the quiet fingerprints of those German engineers who, in the winter of 1944, sat in a frozen hangar outside Berlin tracing American blueprints by lamplight. The B-29 had never flown over Germany. It didn't have to. Its presence was felt through the documents, the reports, and the realization it left behind. That industrial maturity, not theoretical brilliance, decides the course of history. For the men who studied it, it wasn't humiliation. It was education. The war had ended in ruins, but the lessons endured. Decades later, when West German engineers helped design the Airbus Consortium's first wide-body aircraft, the A300, they used modular construction, standardized wiring, and redundant systems, principles born not from European invention, but from what they had once studied in the wreckage of a captured American bomber. The echo of that understanding still lingered. The true future of aviation had been written long before the war ended, in the blueprints of the Boeing B-29 Superfortress. And for those who had seen those drawings firsthand, that truth never faded. One engineer, when asked late in life what he remembered most, didn't speak of defeat or politics. He simply said, "When we examined the B-29, We understood we were decades behind, and for the first time, we wanted to catch up. Thanks for listening till the end. I put a lot of effort to bring you factually correct and lesser-known stories of the past. Subscribe my channel if you like this type of content.